All right, thank you everyone for coming. Today's masterclass lecture will be on Atom Probe Tomography. I hope you will forgive me an overwrought slide transition at the beginning. I couldn't resist. Let's see if I can get it to work. There we go. Wonderful. All right, so today we are going to be doing an introductory lecture on Atom Probe Tomography. This is intended for people who have little to no experience with the technique and are curious about it, what it is, how it works, and what it can tell them. Just as an overview, I'm actually going to begin by, since this is an introductory lecture and this is to some extent an introductory series, introducing time-of-flight mass spectroscopy and tomographic methods, at least in general, to those who may not yet be familiar with these methods because they're essential to understanding what Atom Probe is and how it works. We'll then cover the basics of Atom Probe, the actual equipment, how the procedure takes place, and the data set is generated and handled. Of course, we have to cover sample considerations like all microscopies. If you do not have the correctly prepared sample, you will not get any sort of meaningful data. And then the sorts of Atom Probe work that have been done and are ongoing at CNS, just a small sample because there's quite a bit of it. So, Atom Probe Tomography, what is it? I've written a bunch of jargon terms up here. It's reconstructed time-of-flight mass spectroscopy. What it is a volumetric three-dimensional technique that relies on doing single ion mass spec. In other words, the data set that you receive is a three-dimensional volume containing the location and mass identity of the majority of the atoms in your original specimen, ideally all of them, but at least the majority. It has spatial resolution for the positioning of those species within about 1 or 2 angstroms. It can be a little better, it can be a little worse, depending on your run conditions and specimen. Volumes that one can address are on the order of billions of atoms for a long run. Less than that, obviously, is easier and quicker. This corresponds to volumes on the order of cubic micron, on that order, not necessarily that close order. It is sensitive to every elemental species on the periodic table. Hydrogen analysis is difficult, as it is in all techniques that I'm aware of. And of course, if one of your elements is unstable, that adds some complexity into it. I'm just going to flash up briefly the current official definition, and I'm not going to dwell on it. You can look at the VOD if you want to read through this, but the point of this is just to indicate that Atom Probe is also an evolving technique. It is a technique that is improving and being worked on. Part of that, of course, is developing standards and terminology, which is also under development. So I'm going to start out then by introducing mass spectroscopy. We haven't covered this yet in this series of masterclass lectures. In any analysis problem in material science, you start, I hope you can see my mouse pointer, you start with a chunk of material composed of atoms of different types, and what you are interested in is knowing what types of atoms are in that material and how many of each. Now, one way one can address this is to direct a beam of radiation towards our material, causing it to emit light. This light can then be collected using some sort of light sampling detector, and using our knowledge of the physical process that generated it and our detector hardware and so on, we can turn this into a composition and species list for our piece of material. This is part of a class of spectroscopies we've already heard about a couple of times in this series, photoemission spectroscopies. But what if there were a more direct way, a more brute force way? Say, for example, if our sample were to suddenly explode into its discrete elemental species and separate them out from one another, and we could collect them and sort them by mass into discrete little buckets. If we could do so, we could then count how many chunks of each mass we had, and by understanding where those chunks came from and so on, we could arrive at the same point, a list of different elements, ions, and their quantities. And this category of measurement technique is mass spectroscopy. The mass spectroscopies, there are quite a few of these, including some hybrid techniques. The particular one that we are going to be dealing with today is called time-of-flight mass spectroscopy. It's the one we use in Atom Probe and in some other techniques as well. Again, we are going to start with our chunk of material, and we are going to end, if we are fortunate, with a spectrum consisting of the number of chunks of material, of ionic and elemental species detected with each discrete mass. To get from here to there, The first thing we're going to do is apply some sort of burst of energy to our material. And that burst of energy is going to cause a portion of our material to dissociate and fly away from the bulk. At the same time that we apply this burst of energy, we are going to start a timing device of some sort, a stopwatch, a timing circuit, what have you. Now that these chunks of the original material are liberated, we are going to further apply a potential of some sort and accelerate them away from the original material. After all, we don't want them falling back and sticking to it. That doesn't help. We are going to accelerate them along a racetrack of sorts of known or easily calibrated length. And as time ticks forward, what we will see is that the different species that we have liberated are going to spatially separate. Since they have different masses and are all experiencing the same potential, they are going to experience different forces proportional to their mass. And as time ticks forward, one of them, in this case blue in the middle, will arrive at the finish line of our racetrack first and be recorded on a time of flight spectrum as a single count at one particular time. Time continues and the next one arrives and is assigned, and so on and so forth until all the pieces of material that were liberated by this burst event have arrived on our detector, or we turn our detector off and miss some things, hopefully not. So this gives us a time of flight spectrum, number versus arrival time. Very good. To go from there to our mass spectrum, we take advantage of some very simple physics. We know in principle the kinetic energy that these chunks of material were able to acquire because we know the potential that we applied to the system. We know the time it took for each individual chunk to traverse a known or, again, easily calibrated distance, which gives us velocity. And then we can just plug those in and extract mass. And this is how we perform our mass spectroscopy in this case. Notice I'm going to put an asterisk on the E and the M here because the precision with which we know the actual kinetic energy of the fragments ends up being a major determinant of our ability to resolve mass. Fortunately, in the case of Atom Probe, it's pretty good. Okay, so that's what time of flight mass spectroscopy is. We're going to take chunks of material off, throw them down a racetrack, count how long it takes for them to arrive, and then convert that into their mass. How about tomography, the last word in Atom Probe tomography, and its inevitably associated follow-up reconstruction? So tomography is how we handle trying to analyze objects that are in some way impossible to analyze all at once. The most common reason being that they're three-dimensional, and most of our good analysis techniques are one- or two-dimensional. So tomography, meaning essentially slicing, we start with an object, and we capture a subvolume of that object with whatever our analysis technique is. And we will capture a series of subvolumes, and that will become our data set. Now, inevitably, because no technique is perfect, especially techniques that are destructive, such as the type of tomography we're doing in Atom Probe, there will be some degree of uncaptured volume. This could be large, it could be small, but in any case, it will happen. And so our final data set will consist of a series of discrete measured volumes of the original sample with some degree of gap. It may be extremely small, vanishingly little, but it will always exist. Our job then, having performed tomography, is to perform reconstruction, wherein we take these subvolumes that we have measured and we connect them back up again in a way that preserves information about the actual connectedness in the original object. The simplest way to do this is called interpolation, which is where we make no assumptions at all about missing volumes other than their size. And we simply impose smooth continuity between the measured subvolumes. And that can introduce some artifacts, but it does not introduce any particularly strong assumptions. On the other hand, if we know or believe we know something about the original object, we can use our assumptions about it to perform a heavily biased assumption-based reconstruction, and in a perfect world, use the fraction of the volume that we actually did measure to reconstruct the whole thing. In an imperfect world, of course, we are going to start introducing defects and artifacts when doing that. Atom Probe is going to take advantage during the reconstruction process of both prior assumptions and interpolation at various stages. But it's also quite a complicated procedure, and I'm not going to say too much more about it than this. Just know that it has to happen. So what does that get us? Well, that gets us these lovely three-dimensional data sets, which I'm going to set spinning here. We like to spin our data sets in Atom Probe. So what this gets us is these conical volumes in which we typically display individual atom species color-coded, red, silver, blue, what have you, for clarity. These volumes consist of very large numbers, many millions or more, of atoms all positioned in space, and we can perform all sorts of analyses. Simple ones, such as merely wrapping areas of constant concentration in a surface, as in all three of these examples. More complex ones, such as fully volumetric composition profiles, and so on and so forth. Well and good. So, how exactly do we go about doing that? We're going to take a slightly historical perspective on this. Where did all this come from? How did we get to this point? And we started out quite a while ago with the precursor to Atom Probe, a technique called field ion microscopy. This technique was based on the observation that if you have a sharp piece of metal, a little needle, in a vacuum chamber, and you place a large bias on it, large DC bias, any residual gas atoms that are floating around in your vacuum chamber, there are always some, that contact this needle will become ionized and will be projected away from the surface, which is perhaps not that surprising. But if you put a detector, such as a phosphor screen, in their path, you discover that the pattern that they generate is extremely dependent on local electric fields on the surface of the sample. So local, in fact, that you end up resolving the positions of the atoms on the tip of your sharp needle. This was called field ion microscopy. It was, to my knowledge, the first technique to directly image atoms and was quite a breakthrough. Now, it was noticed that if you continue to raise the potential that you apply to your needle, at a certain point, atoms start to vanish. And it was realized that this meant that they were actually overcoming the chemical bond that was holding them to their substrate and being projected up along field lines, the same as these gas atoms. However, they would only strike the detector once and would be quite invisible under the wash of background gas signal. So the gas quantity was removed as far as possible, and a separate generation of detectors developed capable of directly capturing those projected atoms, because that allows you to actually learn something about the local composition initially of the surface and later of the bulk or specimen. And that is what led us to Atom Probe and eventually to Atom Probe Tomography once reconstruction methods became possible. So the actual setup of an Atom Probe experiment, simple schematic, your specimen, your piece of material, is reduced to a conical structure with a very sharp apex on the order of 100 nanometers or less, ideally. It is placed into a vacuum chamber with very low base pressure, 10 to the minus 11 torr or lower, ideally, to reduce background gas contamination of the mass spectrum and the hit signals. And it is cooled down to cryogenic temperatures. This is both because it improves spatial resolution. Atoms that are warm are by definition atoms that are vibrating around and do not have a particularly useful average position, and also because it helps deal with some other problems that occur during the measurement if you have the sample cool. An actual sample looks like this. This is an SEM image of 1 showing the conical apex, which this scale bar is a bit small, but it's 100 nanometers. You can see that this apex is very sharp indeed. Above the tip is placed a hollow conical electrode called the local electrode or the counter electrode. Here's an image of one of those. And then some distance behind the central aperture of that electrode is placed the detector, which is generally what is called a microchannel plate with delay lines. And for edification, this is what one of those looks like. It is a disc of material pierced by many small channels. The active area of this detector is the pierced channels themselves, not the material between them. Ions or photons that strike within those channels are recorded. Anything that strikes the area between those channels is not. So that's the hardware. Well and good. What do we do with it? So here's what we do. As with field ion microscopy, we start by applying a large DC potential, in this case between the tip-shaped specimen and the local counter electrode, and it is on the order of many thousands of volts. However, we do not wish to raise that potential to the point where atoms overcome their bonding fields and spontaneously evaporate. Because we are doing a time of flight based method, we need to apply a starting signal to actually liberate those atoms. And we do that in pulsed voltage mode, one of the 2 modes of Atom Probe, using a voltage pulsar, which supplies an additional, very short nanosecond pulse of potential to the specimen. That pulse raises the field at the surface of the tip sufficiently to allow a small number, hopefully one ideally, of individual atoms to detach. And upon detaching, they ionize and become positively charged. Now that they are free of the sample and positively charged, the electric field that we've established with this potential serves to accelerate them along the distance between the tip and the detector, passing through the electrode and eventually arriving at this position-sensitive ion detector, the microchannel plate. The voltage pulse acts as our start time signal, and the arrival at the microchannel plate, which is very, very fast readout detector, acts as our stop signal. Well and good. Now, as I mentioned in the previous slide, that plate is not perfectly sensitive across its full area. Because of the necessity of having some actual material to hold all the microchannels, the actual detection efficiency, meaning the percentage of the emitted atoms that can be read out, varies between 30 and 80% depending on what microchannel plate you have, if you have any other optional ion optics in the way, and a few other small details. 30 to 80% is a large range. That variation is primarily based on your instrument model, so it should be fixed on one individual instrument. And although 80% does not sound incredible, by the standards of mass spectroscopy, that is an incredibly good number. Most mass spectroscopies have much, much lower detection efficiencies than that. And by the standards of 3D composition analysis, it's completely unprecedented. Nothing else comes close. Now, this particular method, with the pulsed voltage being used as our trigger signal, is intended for use on conductive materials at low temperature, which means basically metals. Sample preparation can be quite easy for these, at least comparatively easy, and the actual operating conditions for the instrument are fairly straightforward. It is not as useful in this mode for semiconducting and insulating specimens, because although it is possible to insert this high voltage pulse into those needle-shaped tips, it's extremely difficult to extract it and return to the base potential because of hysteresis effects. Obviously, we need that voltage to turn back off, otherwise atoms will continue to be emitted and our start signal will become a fuzzy start window and our mass spectrum will look bad. So for those materials, instead of using a pulse of voltage, we use a pulse of light from an ultra-fast laser, pico or femtosecond, and these days it is most common to use a UV wavelength laser of some sort. That laser pulse strikes the tip. It serves as our start signal. The tip is then energized both electronically and thermally, and this additional energy serves to overcome the bonding potential well that holds the atoms on, and they ionize and fly off, and from there everything else is the same as it ever was. This method is intended for use on semiconductors, insulators. It also works just fine on metals, and in fact is probably the more common way of performing atom probe, at least in research settings these days. However, it does introduce some additional sample prep considerations, and it adds another tuning parameter when you're actually running the instrument, with quite substantial implications for your data quality. Okay, so that's what's going on inside the box. You start with a sharp conical specimen and a nice empty data set, and then after some time, you have a shorter, blunter specimen from whom the upper atoms have all evaporated. You have a data set consisting of a record of the hit locations on our microchannel plate of ideally all or 80% of the atoms from this volume, each one tagged with the time of flight. You can use those times of flight to generate a mass spectrum like this one. And then between the mass spectrum and the position data and the order in which the atoms arrived, you can perform a tomographic reconstruction and generate a nice three-dimensional volume. Obviously, some assumptions will be involved in that, and the process of reconstruction is, as with all tomographic methods, somewhat involved, but this is the basic procedure. I've noted here that collection speed for the data is generally in the range of a few million ions per hour. You can go faster, you can go slower, but that's the sort of order of things. I also am going to put this in because I get to ask this all the time in these talks. Yes, this does work on 2D materials if you want to go to the effort of getting them into a conical volume, which usually involves adding a lot of material on both sides. That is a tremendous amount of effort, and I have not seen any really excellent results from it yet by anybody, but it is in principle possible. So that's the Atom Probe process and how the data set is arrived at, is it right for your material? Well, sure, if your material meets some of these criteria, if it is a solid, no gases please, if it is reasonably stable in air and vacuum, certainly in vacuum, we can handle air stability to some extent, and we'll be able to more in the future, and under ion and electron beam irradiation, since most sample prep is going to rely on those techniques. It is appropriate if you're looking for an absolute composition measurement with very high accuracy. Note that this is not easy to achieve in oxide or 3,5 materials for a variety of reasons. But if you're looking for relative, meaning spatially relative, composition variations from one area to another, then we can include oxides and 3,5s again without any trouble. It works if your material is either homogeneous, meaning more or less the same composition everywhere and just want to measure it, or more likely heterogeneous, but you can target the different areas that you want to measure directly using our sample prep techniques. And ideally, you would like to have enough of your material to actually perform a few focused ion beam-based sample preparation procedures. Atom probe is not so appropriate in the case that your material is porous, unstable in some fashion, or, and this is an interesting gotcha, has low temperature phase transitions, since we will be cooling this thing down after we have generated our needle-shaped geometry. If it phase transitions while cooling, that tends to distort the needle. It is not necessarily appropriate if you're looking for absolute stoichiometry in oxides or 3,5s. It is difficult if your material is heterogeneous on the micron scale, because it is very difficult to capture all of that heterogeneity in one atom probe measurement. You'll have to do either very many of them or know a great deal already about your material and select the most important area. It is not ideal if your element of interest is present below part per million level. We generally quote part per million sensitivity for the atom probe, even in larger data sets. And it's probably not the best idea if you only have one teeny tiny little grain of this material extant in the whole world, since both the sample prep and the measurement are destructive. Okay. I'm going to put an asterisk next to these ice cubes. There is development work being done on cryogenic atom probe transfer, allowing frozen specimens to be moved to and from the instrument. We are not currently equipped to do that at CNS, but if you're interested, I can get you in contact with people who are. So sample prep. Sample preparation for atom probe generally takes place inside the focused ion beam dual beam instrument. We have two of those at CNS, as you heard in Stefan's talk last week. Either one is capable of performing this procedure. For the sake of clarity, I've got a little cartoon here of a chunk of material with some little orange dots, which represent our features of interest that we are trying to get into the atom probe. Using the focused ion beam's internal deposition capabilities, we deposit a protective layer of material over our region of interest so that it is not destroyed or modified by all the ion beam milling we're about to do. Here's a little SEM image of what one of those layers might look like. And then we use the ion beam to begin to cut away the material on both sides of our protective bar. Unlike for TEM specimen preparation, for atom probe, we generally perform these cuts at an angle, producing a chunk of remnant material with a triangular cross-section. Very good. And there's an SEM of that in the upper corner as well. We then free one end with a cross cut, producing a triangular cantilever, and bring in the micromanipulator probe that most modern FIBs are equipped with. We attach that to the free end of the cantilever using deposited material and cut the final end free, allowing us to lift out this triangular bar from its host substrate, containing undamaged your features of interest in the inside. We then go to a pre-made support post. The most common are these sort of pyramidal and post structures. These have to be made of a conductive material. Their purpose is to elevate your material away from the holder and the background substrate such that your piece of material is the tallest object around. We don't want anything taller, or the taller thing will do atom probe and not your sample. We buy these pre-made from a supplier, and they're somewhat expensive but not too bad. We bring with the micromanipulator needle in the fib our bar of material over to the top of one of these posts, land it on top of them, and then glue it with a little patch of our fib deposition material. We can then cut right next to that patch, freeing both the attached piece, which is stuck to the post, and the bar itself, which can then be taken to the next post in the row of posts, and we can make more and more and more atom probe tips from one lift out, which is very efficient. So this leaves us with this structure, a little triangular chunk of our material containing a feature of interest welded to our post, and you can see an SEM of 1. It's been welded on both sides for stability. We then bring the ion beam in from above the specimen in a series of circular cuts, causing the triangular piece of material to be reduced to a conical needle. And these little bright triangles left at the bottom are what is left of the welds that we applied early on. Very good. So in close-up, this is what one of these needles would look like, and your concern in producing these is to position the feature of interest within the easily accessible volume of this needle, which means close to but not at the upper apex. Throughout the last parts of this positioning, where we are producing this final cone, we use low voltage focused ion beams, meaning low accelerating voltage on the ion beam, to minimize surface damage and implantation. We can handle those problems to some extent in data analysis, because being a volumetric data set, we can see the gallium implant and try to exclude it and the area around it, but it's better to not destroy portions of your specimen to begin with. The volume that is easily analyzable is going to depend on your sample material, but as a rough rule of thumb, the top 200 nanometers of any well-made needle should be within the range of what you can analyze, a micron or so in really well-behaved materials. And we need to position our feature of interest, as mentioned, in that volume. If it is near the lower edge of the volume, we may not be able to complete a measurement of it before other things happen. Obviously, if it's down near the welds, we're never going to measure it because we can't go that far down the needle and the welds don't run properly. And there is always the risk, if we overdo our milling, of milling our feature of interest out of existence. So a certain amount of care must be taken. Fortunately, we have some tools to help us with this. In addition to the full suite of standard SEM tools, our Helios fib has also backscatter diffraction built in, which allows crystallographic features to be directly imaged and mapped inside these tips. This is an example of a diffraction pole figure map taken from one of these tips that has one grain near the surface, which is green, and another grain further down, which is slightly visible as yellow, and a dark green boundary between them. As this tip was reduced in diameter and shortened, the clarity of the backscatter image increases, and you can see the grain boundary, which is our targeted feature, very clearly. And we can continue the milling process until that grain boundary is within the easily analyzed volume near the surface of our atom probe specimen. So we then take our delicate, carefully prepared needle over to the atom probe and we run it. And in a wonderful world, we get millions to billions of atoms. And hopefully we see everything we care to see, and then we turn the instrument off and take our blunt needle back out. More commonly, what happens is we run and run and run and get as much data as we can until an event called fracture occurs. Fracture, the exact phenomenology is not really well understood. It's a very fast procedure occurring at high voltages and high vacuums. But essentially, it is the destruction of your specimen caused by the large potentials and strains that are being applied to it. If your specimen is poorly chosen, meaning if it is porous, if it has some sort of mechanical weakness, like a crack, or a poorly adhered layer or something like that, then fracture will occur earlier. If your material is a piece of stainless steel, fracture should occur later, but it will always occur eventually if you continue to run forever in the atom probe, and it will convert your specimen into, well, this sort of melted splat and a terrible mess all over the local electrode. So we aim to achieve our intended measurement before that happens. So on to some examples then of atom probe measurements that have been done at CNS. The first one is fairly simple analysis, or at least it starts out simple analysis of grain boundaries in a mineral. And this is just an example of how we can use the atom probe plus the power of our focused ion beam systems to target specific features on a sample and analyze them in a way that simply can't be done with any other technique. The sample in this case was some deformed, deliberately deformed, Olivine-Clinopyroxine mixture. Experienced a phenomenon called diffusion creep. It has, as we can see in this backscattered SEM image, two different phases, one light, one dark, with many grain boundaries between them, and also a fair number of voids, which had to be avoided. We targeted for lift out a specific set of grain boundaries between olivine grains and Olivine-Clinopyroxine grain pairs. The idea being to see what sort of compositional variations were present on those grain boundaries. Sample preparation, just similar to what you've seen, was fairly straightforward, produced a blunt needle, which was gradually sharpened up until we finally had a very, very sharp needle with very small apex containing the grain boundary of interest in the analyzable volume. This was repeated for a number of tips with the same lift-out bar so that we could catch different grain and phase boundaries, and the atom probe analysis revealed chemical partitioning at those boundaries. In other words, specific elemental species were segregated to the grain boundary. In the case of olivine, quite a few of them, aluminum, calcium, sodium, and chlorine. In the case of clinopyroxine to olivine, it was a little less obvious because there's quite a bit of aluminum, calcium, sodium in the clinopyroxine, but the chlorine is clearly segregated. So that's nice. We can now see these grain boundaries in the chemical imaging, and that's very attractive. But what we can do that can't be done any other way is determine the actual widths of these chemical segregation phenomena at these boundaries. We can do that by going into those boundaries either with a simple one-dimensional plot across them or using a more complex curved surface and plotting along a not flat grain boundary. And we can actually determine the chemical width over which things have segregated during the deformation process. And this has implications for the field of rock mechanics and petrology, which we're not going to discuss here. But given that what we are talking about is concentration changes on the scale of less than 1% over a length of 3 or so nanometers, you'll begin to see why this is the kind of measurement that can only be done with this type of very granular atom at a time local composition technique. Well, okay, how about another one that doesn't rely on crystallographic grain boundaries? This is a 3,5 material, aluminum indium phosphide, with local stoichiometry variations. They're quite subtle, but quite impactful. This particular piece of material was grown with, or attempted to be grown, with a targeted composition listed up here, 0.47 to 0.53 cation ratios. But it was grown at several different temperatures in a stacked fashion. And what was noted was that depending on growth temperature, the luminescence that this material gave off corresponded to very different compositions than the one it was intended to be grown with. Now, TEM imaging of the layers showed a sort of mottling within the aluminum indium phosphide, which could be composition or could be phase, since TEM images both. Dark field STEM, which is a purely mass contrast imaging technique, shows very faint composition variations within the measured volume, but attempting to extrapolate those to actual composition fluctuations, we end up with composition fluctuations which are at most on the order of about 2%, far too little to correspond to the photoluminescence effect that was being seen. So it was clear that whatever was going on was too local an effect to easily analyze with a transmission technique like dark field STEM. We turn to atom probe tomography. This is an aluminum map of the analyzed volume, and you can see quite substantial fluctuations in aluminum content over the area that we're analyzing. The TEM data that we showed with its fluctuations is taken from a TEM lamella. And TEM lamellae are thin membranes of the original material, but they are not of infinite thinness. They have some finite thickness. In this case, they were about 70 nanometers thick. And if you imagine a transmission measurement that passes through this volume and out the other side, it is going to average together all the fluctuations that one can see over 70 nanometers. And that is why the extracted fluctuations were so small. However, this is volumetric data now in Atom Probe. We can slice it however we want. So if we were to, for example, take a 5 nanometer thick slice and bin that in one dimension, we extract fluctuations like this, where we can see the aluminum bouncing up and down over a full 10% range, which is now getting much closer to the quantities that we were seeing from photoluminescence. That, of course, is trying to directly compare it with TEM, but Atom Probe can do more. We can actually look at a 2-dimensional contour plot within that 5 nanometer thick slice of our data. And we can see it over very short distances. This is a plot of aluminum content in 2 dimensions. Over short distances of only 10 nanometers or so, the aluminum fraction can vary from 0.25 all the way up to 0.5. So an enormous variation in aluminum content over very short distances that wasn't resolvable with any other technique. This is the result of some spontaneous phase separation that occurred during growth and is all well and good. Just a complete thought experiment of comparing this to TEM, by the way, if we take this slice of ours and we thicken it from 5 nanometers all the way up to 70, comparable to that TM lamella that was originally analyzed, we see that the fluctuations begin to average out until they approach those seen in dark field STEM. Okay. So that's some bulk and grain boundary analysis. How about an engineered interface? In this case, is going to be the interface between a semiconductor and an oxide. The semiconductor is silicon. The oxide is a transparent conductive oxide class called aluminum zinc oxide. This is a very attractive class of materials technologically, but it suffers from an issue in the case of silicon, which is that when metallic substances, metallic layers are present on the surface of a piece of silicon, you get a phenomenon known as Fermi level pinning, which is undesirable for a bunch of applications. So in this particular case, the aluminum zinc oxide that was deposited was doped with aluminum still, but not to the level of being conductive. It was below the insulator to metal transition. And Fermi level pinning was still seen. Why? Okay, so we take out a chunk of the material at that interface. Here's the atom probe tip showing the lighter colored oxide on the surface. We perform atom probe, and we get an atom probe data volume. And here we are spinning it as normal. Note that the interface, in this case, where the green transitions to the gray of silicon, is not level. It's not perfectly normal to the long axis of the needle. Fortunately, since this is volumetric data, that doesn't matter. We can rotate our analysis volume however we want. If we take this data and we look at aluminum content, since aluminum in the system would be one of the major determinants of conductivity and metallicity, we note that for most of the film, aluminum content was relatively stable, but right at the interface of the silicon, it shoots up to very high concentrations of aluminum. And what does this mean? Well, for starters, it means that there's a thin little layer right at the interface, which would have been tremendously difficult to measure with most other techniques. Most chemical sensitive techniques have a great deal of trouble measuring interfaces. From a technological standpoint, what it means is that even though the bulk of the film was insulating, right there at that interface, the aluminum content was high enough to cross the insulator to metal transition and actually render it conductive, which is presumably to blame for the Fermi level pinning effect. And this was true across a wide range of slightly differently grown zinc oxide films and silicon substrates. They saw a metal-like composition at the interface. Well, that's one interface. How about a whole lot of interfaces packed close together? In this case, interfaces inside of a structure known as a quantum cascade laser. Quantum cascade lasers are a semiconductor structure consisting of a substantial number of discrete composition films grown epitaxially on top of each other in such a way that when electrical bias is applied, they emit laser light at a designed wavelength. And these things are designed very, very carefully and very precisely to produce a specific output light. However, if the interfaces between the different layers are not perfectly abrupt, if they are smooth, sloped, graded, then the light emitted will be of a different wavelength than the intended emission light. And given that these are technological devices with specific applications in mind, that is undesirable. However, the degree of that grading and the length scale over which it occurs very sensitively determines the shift in emission wavelength and is fairly difficult to actually directly measure. So, for this particular chunk of material provided by Lincoln Labs, they provided us a test structure they wanted analyzed containing many repetitions of a quantum cascade laser stack. We take it first to the TEM and look, and we can see the discrete layers, but we notice that they are not atomically sharp at their interfaces. There is some blurring, some fuzzing. However, both TEM and STEM, EDS, and so on measurements have about a 1% atomic concentration floor on their measurement ability and do not have enough spatial resolution on that composition map to easily distinguish aluminum and gallium atoms over the scale necessary to work out what kind of composition grading was going on. Fortunately, Atom Probe does. So we take this material, we make our customary little Atom Probe needle, and we do a rather long Atom Probe run to capture 16 repetitions of that structure. Here they are. We don't want to look at all 16 at once, so we'll just extract one. And here it is with aluminum and gallium displayed, gallium in red. And what we can see is that indeed these are not sharp transitions from one phase to another. They are relatively sharp on one side, the growth direction being bottom to top, but then heavily graded on the other. And there are a substantial number of individual isolated gallium atoms floating around in layers where they are not supposed to be. We can compare this directly to theory and use it to work out the degree of grading that occurred and find that it matches up rather neatly with what would be expected given the luminescence behavior of this material. It's all very nice. And just to hammer home the point, here is a one-to-one comparison between the TM image and the Atom Probe image. And we can see that there is a degree of roughness in these films visible in TEM and in Atom Probe both, but these discrete gallium atoms in the interstitial aluminum layers just aren't visible at all without a technique like Atom Probe that is one atom at a time. Okay, so there's a bunch of different, fairly well understood material systems being probed a bit farther. How about a completely non-understood, complicated three-dimensional small-scale material system, a metastable form of silicon that was formed over ultra-fast timescales. This is a class of material known as rapidly solidified material. It is a piece of silicon with far above solubility levels of impurities injected into it that was melted and resolidified over the course of nanoseconds. And on the surface, in SEM, we can see it forms a very strange square texture, which was not well understood. It was assigned the term cellular breakdown. And in cross-section, in TEM, there are these pseudo-linear structures with lots of little blobs around them within about the top 140 nanometers of this, which are presumed to be segregation regions of the impurity. However, upon doing diffraction work on that layer, no additional diffraction spots other than those from crystalline silicon are detected, meaning that these are not precipitates in the traditional sense. They are not their own separate crystalline phase. It's sort of a cartoon vision of all of this, but what exactly they are, what they're composed of, what their shape is, what their boundaries are, was not known. Enter Atom Probe, which reveals them to be these lovely, rounded, filamentary structures with occasional detached droplets. So that's very nice. This is the sort of the first measurement of the actual structure of these. But we also want to know composition because this is a technologically interesting material, and we need to understand its composition both within and without these structures in order to understand how it behaves. Other attempts to measure the composition of this were performed, of course, using other mass spectroscopies, such as SIMS, yielding the blue curve here. But since those averaged out both the sort of silicon-rich matrix and the segregation structure, they missed a lot of the fine detail. This is a direct comparison. If we just take an Atom Probe data set, slice it, and then average the contents of each slice together, we get the red curve, which, as you can see, reproduces the shape of the blue one very nicely, since these are both mass spectroscopies, although because Atom Probe is a smaller scale, more granular technique, we get some small excursions. But what we really care about is treating these two regions, the very blue and the not so blue, as separate materials, so we can understand how they might perform both separately and together. And the nice thing about Atom Probe is that we can wrap those regions in a concentration surface and separate them out as two separate data sets. And when we do so, we find that the matrix of silicon has a nice, clean, diffusion simulation matching content of the impurity, which is cobalt for this particular study. But the filamentary structures themselves have a much, much higher amount of cobalt in them, and again, show some granularity because in the depth of that tip, there were different amounts of the filamentary material. We can open them up and perform concentration profile plots of different sorts, like these contour plots, which actually exposes some of the internal dynamics of these filamentary structures. We can see areas like these marked with asterisks where the composition actually decreases considerably in cobalt. This is because these were actually liquid at one time and they were undergoing a Rayleigh instability, which was causing them to begin to neck off and form droplets, but then they froze. All quite intriguing. It's a case where Atom Probe gives us the ability to look in depth into a very unusual material about which very little was known, that was formed through the result of both small scale and fast time processes. And the sensitivity of Atom Probe is sufficient that we can actually start to say something about those processes from these data sets. Now, at CNS, we are an open research facility. We are committed to analyzing whatever our users bring us. insofar as that's possible and reasonable. So just a few more things that people have brought through the door, not even the wildest things people have brought through the door. Allende meteorite CAIs, calcium aluminum inclusions. These are some of the oldest known materials in the solar system. They were formed, we believe, in the protoplanetary disk that condensed around the sun during the very earliest stages of solar system formation. They contain inside these inclusions little metal nuggets called refractory metal nuggets, whose composition and interfaces in principle say very interesting things about the early stages of planetary formation in the solar system. And so one of the planetologists brought some of this in to look at these refractory metal nuggets and find all sorts of interesting elements that you don't see much like ruthenium, segregated to grain boundaries and involved in various crystal grains. There was another interesting material was some indium aluminum arsenide grown with germanium, which is not soluble in that material, and segregated out to form embedded nanowires. Depending on the growth speed with which this material was formed, these nanowires had slightly different geometries. Very slowly grown ones over here on the right, I should look in cross-section, formed large ovoid structures. As growth was sped up, these structures became smaller but communicated with each other via a little bit of germanium exchange. And then with very fast growth, they were much smaller and much more isolated. And this is believed to be the result of some surface segregation occurring during growth. Another very attractive material that was brought in, these are beads of volcanic glass from the Shorty crater on the moon, which were brought back by the Apollo 17 mission. These were formed during the very, very early stages of the moon's existence when it was molten and had volcanism. And as these cooled and condensed, they captured both the primordial atmosphere of the moon and its primordial magma. Their surfaces, here in cross-section in backscatter, which is mass contrast imaging, have both a thin coating of interesting elements as well as some embedded, bright, in this case, heavy element structures, and some odd things growing down into the glass itself. Higher resolution with the TM, actually with the stem, we can see that there are these dendritic branched crystallites that have formed inside the glass, therefore presumably after the glass had cooled, over the course of the billions of years that these beads lay on the surface of the moon. And their composition and formation mechanics were not well understood, so we've taken these apart and atom probed them. It turns out that these dendritic structures most closely match olivine again. They're a titanium-rich silicate, and they have very rounded edges on them, which has a bunch of interesting implications for how they formed and how they nucleated. Another material that came in, catalytic nanoparticles. Copper, in this case, doped with a very small amount of nickel. These were actually present in the form of aggregates, which are a tricky sample to prep because they tend to be porous and possibly mechanically weak. We did develop a method for making these actually usable in atom probe, performed atom probe on it, orange copper, and in this case, green is a copper oxide. And if we look into the data set, and I'll just pause this in a sec, there we go, we can see the actual boundaries between discrete nanoparticles inside this aggregate. This means that we can, using our wrap in a surface trick, extract individual nanoparticles and their grain boundaries and learn about their composition. We also note this segregated green is actually an oxide nanoparticle, not a continuous oxide film nor continuous oxidation, but a discrete particle of oxide, which is of interest for catalytic activity. And finally, just one more very interesting material that has come through our door was of the class of topological insulators, an iron-tin mixture, analyzed very attractively on our JOL ARM transmission electron microscope. This material possesses what is known as a Kagome lattice, where one of the components falls on the corners of a bunch of connected triangles, found hexagonally sited second atoms. We took this apart for atom probe, and we used a trick that one can perform in these data sets, where we take a density plot of the atoms inside of our crystalline samples data set. Because of the presence of discrete atomic steps on the surface of our tip as it evaporates, the electric field lines actually direct atoms away from the surface in a slightly non-uniform manner, producing these lovely crystalline pole figures, very similar to what you get from diffraction methods. In this case, reproducing the triangular aspect of the Kagome lattice very nicely. if we go into the center of this pole figure and take out some data that was aligned very nicely with a low index crystal plane, we can actually see the kind of resolution Atom Probe can achieve when it's working quite nicely. Rotate this up so we're on edge, and we can actually see the discrete crystalline planes in one dimension of this particular material. We then separate those planes out into their distinct species and begin to take some sort of statistical measurement of the sighting of those atoms on the lattice. So, brings us to the end of our examples and our summary slide. The takeaways here: Atom Probe is a volumetric, one ion at a time, time-of-flight mass spec microscopy technique with sub-nanometer composition and structure resolution. It can tell you a tremendous amount about your samples. Sample preparation is generally the big gatekeeper for this technique. It requires focused ion beam expertise, and the advantage to that, of course, is that it permits site-specific feature analysis. We can pull out one transistor, one grain boundary, one very small chunk of corrosion material. Pretty much if you can see it in the fib, we can hit it and do Atom Probe on it. The data sets acquired can be billions of atoms, millions to hundreds of millions are more typical, and they achieve part per million sensitivity across the whole periodic table. Making a good choice for your material and your planned measurement is going to be critical to getting a good quality data set and answering a specific limited scientific question. And this is, of course, true with any of the techniques that have been discussed or will be discussed in this Masterclass series. In the case of Atom Probe, the restrictions we've already gone over are quite important. Unlike other techniques, because of the issue of fracture in Atom Probe, if your material choice or specimen preparation are not very good, you will not get bad data, you will get no data, you will get a fracture event and a mess on the electrode. And then all sorts of different types of analysis are possible on your sample with a well-performed Atom Probe measurement. I've gone over some of them, but there are many, many, many more, and I am happy to talk to you about your particular measurement needs. So that brings us to the end of the lecture, and if there are questions in chat or elsewhere, I would be happy to take them now.